Okay, so my name is Sergio. This talk is about an introduction to BitVMX, a CPU for universal computation on Bitcoin. And what I mean by computation on Bitcoin is using Bitcoin without any change, without any soft fork or any hard fork. You can find me on Twitter and Sergio Lerner, and what I do is science research in Rostock Labs. Rostock Labs is the main contributor to the Rostock sidechain, and also I work for Fairgate Labs, which is a research pioneer in privacy-preserving technologies and especially in multi-party computation. So what's the motivation? Why we started looking into this new invention of BitVM? Well, we created in 2015 the Rostock sidechain, the first Rostock sidechain, which is the largest and longest running Bitcoin sidechain. And it's merge mined with Bitcoin with more than 60% of the hash rate of the Bitcoin miners mining Rostock since 2018 when it was launched. It's fully aligned with Bitcoin, like the native currency of Rostock is Bitcoin and no other token, and contributes to the security of the security budget of Bitcoin by providing transaction fees to Bitcoin miners. So we developed for Rostock the two-way peg, what we call the POW peg. This is really the evolution from a standard federated multisig into something that is much stronger in terms of security. We have signing keys that are participating in this multisig secured by HSM devices, hardware security models, that they are tamper-proof, state-of-the-art technology in there, secure elements base. We have a 5 out of 9 signature threshold. These HSMs are running Rostock-like clients inside, so you cannot extract a private key, you cannot make them sign anything you want. They sign whatever is backed by an enormous amount of cumulative hash rate. And we have public firmware attestation, like anyone can check the firmware of these devices. So this is great in terms of security, but in terms of decentralization, it just gives, you want this to be permissionless and that anyone can participate securing this peg. And we could do better. We have been trying to do better since we launched Rostock in 2018. So for us, the discovery of BitVM was a huge event that said, okay, we can now try to do something better. So first of all, why should anyone try to compute in a blockchain, right? Maybe this is not necessary to compute. Well, there are proven use cases for computing on the blockchain, like smart wallets, where you want to set up your own thresholds or whitelists or additional keys. Obviously, decentralized exchanges, we want to have DeFi embedded in the blockchain and not in a centralized exchange. Decentralized organizations. Improved Lightning network channels. I know there are many Lightning developers here, and what you could do if you have a little more computation is just create any type of Lightning channel in Bitcoin. You could build more decentralized bridge for sidechains such as Rostock or rollups. You can verify the state transition of rollups in Bitcoin, which basically makes rollups really allowed to exit the funds at any time. And maybe you can have a new idea for a new L2 and verify that on Bitcoin. But I'm particularly interested in these last 4 use cases, especially bridging with sidechains. Why? Because Bitcoin itself, it's a store of value, and trying to make it more, responsive doesn't make sense at this point. Like, it's much better to work with a sidechain or a rollup where you can have a 5 seconds interaction with the blockchain, and you can have a more better user experience for DeFi. And also, Bitcoin is becoming very expensive. So if we can move the payment thing into a sidechain or a rollup, then this would be great for Bitcoin. So I'm particularly interested in decentralized bridges. So to tell you how good is Bitcoin in terms of computing, I bring this slide. Do you know what is this? This is the Charles Babbage mechanical computer, the analytical engine. It was never actually built by him, but it was designed in the 80s, and it had 16 kilobytes of RAM, and it could do addition and subtraction in a single step, right? Quite a powerful machine. And you're young, but maybe some of you have played with the Atari 2600. I did when I was a kid. I played a combat game. And this machine had 120 bytes of RAM, but you could have with banking, you could have 64 kilobytes of ROM, but it could do addition, subtraction, division, multiplication, bitwise operation just in a single instruction. It was super powerful. But now we have Bitcoin. How good is Bitcoin compared to these machines? Well, in theory, we have this stack that has 0.5 megabyte of space. We have this tape, which would be the script pub, the program, that can go up to 400 kilobytes in a standard transaction. And we have very limited instruction, like we can add, subtract, and check a signature. But if we want to use Bitcoin, as is today, as a general purpose computer, it turns out that the stack, it will finally be holding 1,000 bytes, because you will finally be operating on bytes, and you only have 1,000 elements in the stack, so you're super restricted. And the tape, if you want to do multiplication and you have to implement that by hand, then the whole, I mean, let's say you want to do a snark verification, which is full of multiplications, then it goes down to about 20 kilobytes of real instructions. So you add this bitwise operation, but you end up having a computer that looks very much like the Babbage computer that showed. And of course, we have this problem of the opcodes that have been disabled by Satoshi, like most of the arithmetic operations, the opcat, of course, bitwise logic would be super important if you want to implement like a hash function in Bitcoin script. So you are very limited. So computation on the blockchain is expensive. Like executing 10,000 opcodes in the Atari 2600 would cost that amount of dollars in electricity, like less than a millisecond. And in Bitcoin script, the day I checked, it was more than $200. So there's a huge difference between computing on your personal computer and doing that on Bitcoin. Yet, we still want to compute some things, very small things, on Bitcoin. So it turns out that Bitcoin, thanks to ChatGPT for the image, it turns that Bitcoin is a kind of a calculator that only does addition and subtraction and has this fantastic button, I would call it play Tetris, where it does a lot of functionality, which is actually the check sig, but it's super restricted. Some people have tweaked check sig to do something else, like oracles and discrete log contracts, but essentially it's like very limited. So how can we compute on a blockchain and on Bitcoin in particular? Well, there are many models that have been pop up during the years. So we have the off-chain trusted computation model. This has been tried many times, like having oracles doing the computation and then voting on chain. Of course, we are not interested in this because this is not really decentralized. We can have Bitcoin script model where we have a non-Turing complete machine and it's bounded by the space of the program. So that's Bitcoin or Litecoin. Then we have the meta computation. This is what Rootstock and Ethereum do. Like, you are allowed to create any kind of programs, Turing complete programs, but we are going to charge you for everything you do. We have this new, well, not so new idea of proof of computation integrity, where we don't actually run the whole thing, the whole program, but we just first create a proof that the program works, and then we just have to verify the proof. And that is the snarks, starks, and have been implemented successfully in Zk rollups. And then we have this final model, which is the disputable computation, sometimes called optimistic computation, that it was pioneered by TrueBit, and it was used also in rollups, and Robin brought this to Bitcoin with BBM0, the tap leaf circuits paper, and then he improved it with BitVM1, Now he's working on BitVM2, and we took that as a base foundations to build BitVMX. So what is happening with all these different projects? Well, BitVM0 is a kind of proof of concept, like a theoretical result. Nobody will ever write a snark verifier in logic gates because it takes terabytes of data and billions of gates. Then there is the BitVM1 CPU. This was the previous projects of Robin, and it's now deprecated in favor of BitVM2, which is under development now, so we don't have something to play with. And also there is no paper on this, but he's preparing one. And we decided to take the idea of the CPU, the general purpose computer, and create BitVMX, which is basically a meta CPU because it allows you to create any kind of CPU. But we are, in the first project, we are focused on implementing a RISC-V processor. So to give you an idea of how it would be to do a dispute resolution in Bitcoin, probably most of you already know this, but for the new ones, we have two parties here. Patrick, which is the prover, he wants to prove that certain program given certain input verifies and accepts that input and can release the funds. And we have Valerie, which is just an observer that she follows the consensus rules. And so there is a verification program that is actually our script pub, and this is put on a standard output and is verified by the input given the input. So it's very simple. Then we have the snark idea that instead of doing the whole computation, we will just create the verification program will be just a function that verifies the snark. We will take the whole program and we will prove the program works with a small proof. And what we actually verify on chain is a small proof. And we think the first thought is, oh, maybe we can use that on Bitcoin. And this was what Gregory Maxwell thought in 2013. So he actually was one of the first to bring this idea into Bitcoin. He called it coin witness. And he said, okay, when these systems have evolved, we will be able to bring this into Bitcoin. That never happened, but maybe one day it happens. But the problem is that even if we could verify a snark in Bitcoin script today, it turns out that the verification program for Bitcoin script does not fit into these 400 kilobytes. Like the full computation, of course, it doesn't fit. The snark computation does not fit either. So we are stuck. So here's where the disputable paradigm comes. So the idea is now Patrick is the prover, but he's also a responder to certain challenges. And Valerie, instead of having a passive role, she will become a challenger. So Patrick will say, okay, I want to take the money from the UTXO, and Valerie will verify this locally, and if the computation is wrong, she will actually participate in a dispute resolution protocol. So what we have is a protocol that takes several transactions, and there are several script pubs, several programs run in each one of these transactions, and these transactions are pre-generated, like if it was a covenant, they are pre-generated by a certain committee. They throw away the key, so nobody can, generate another key for this committee, and then they can execute the protocol. In our particular case, we are now working in the two-party case, so we don't care much about this covenant thing because the two-party will collaborate creating the transactions. So very simply, the protocol goes like this. There is Patrick. He says, I'm going to withdraw the Bitcoins. This is the program input that makes the program accept. Then Valerie will run this locally, and she say, okay, no, you're a cheater. She knows it because she ran and knows the result locally. Let's resolve this dispute on chain. So what Patrick will do in the BitVM1 protocol, he will Merkleize all the steps of the program, and in each one of these steps, he will Merkleize all the RAM. So basically now they can do a binary search on this data structure and find the step that is wrong. So Valerie will say, okay, tell me the mid states, the hashes of all these particular intermediate steps. And Patrick will give her the mid states signed. And so Valerie finds the wrong step, and then she can go into the blockchain with the signed inputs and outputs that Patrick has signed and the step number, and just evaluate that on chain. Just simple step of the whole computation. And of course, it's billion times lower amount of computation. So in comparison, we can actually verify a RISC-V step with 1/4 of the size of a standard taproot script size, like 400 kilobytes. So this is feasible. So now, what's the novelty here? What have we been working on? So we've been working on a new implementation and a new design for this kind of CPUs, different from Robin's. And the aim of the whole project is not only to publish, but to create an implementation that is secure, extensible, open source, peer-reviewed, completely agnostic, that you can use for any kind of project, to do this on Bitcoin. And there is 2 organizations we have committed time and funds to make this happen. Of course, the project is open source and open to the community to collaborate. We would be super happy if you want to code with us. Now I'm gonna dig into the protocol and I'm gonna mention the building blocks. What are the things we need first to know to do the protocol? So one-time signatures. Because we cannot use ACDCA or Schnorr signatures because there is no check6 from stack, we must implement our own system for signatures. And this is something that has come up in many other, from other people, is using Lamport signatures. And these are one-time signatures. So it's basically as easy as a public key signature scheme. There is a key generation, sign-in algorithm, and a verification algorithm. The only restriction is that you don't sign 2 messages, different messages with the same public key, just one. That's the only restriction. And the size of the messages tend to be long. The size of the signatures tend to be long, and the public keys too. So how to use 1-bit Lamport signatures to do these one-time signatures? So essentially, the public key is 2 hashes, 2 hash digits. Let's call them Q0 and Q1. And the private key is the 2 pre-images of these 2 hashes. Let's call them P0, P1. So it's just very easy. If I want to sign bit 0, I just publish P0 and never publish P1. And if I want to sign 1, I just publish P1. And it's very easy to verify. I just hash and check if it matches Q0, Q1, or if it doesn't match anything, then it's not a valid signature. It turns out we can implement this in Bitcoin script. It takes a fair high amount of bytes, like 32 virtual bytes per bit, including the input, because the input is a hash, and then you have to test. So the signatures become a bit longer. But we can do better. And this is also an idea that several people had at the same time, is instead of using Lamport signatures, let's use Winternit signatures. And Winternit signatures, what they do is, instead of signing bit per bit, they pack many bits into a single digit, and then they sign the digit. So they build a hash chain, let's say with L steps, and to sign any one of these steps, it just gives the intermediate slot on this chain. Okay, so the last pre-image is, let's say, call it 0, and the last one is L, or the reverse, whatever, and then you basically can give away one of these intermediate hashes. Of course, you can forge signatures, and so there is a mechanism that is called the checksum to prevent an adversary from using the intermediate hashes. I call it the pulley, which is basically having a checksum that has the inverted sequence. So if you want to try to fork one, then you are forced to give the preimage that you don't have. Very easy, okay? And when you implement this in Bitcoin script, you can do 25 virtual bytes per bit. So that's much better. Still not perfect, but it's better. So now we have a mechanism to sign data in Bitcoin script. This allows us to create stateful protocols on Bitcoin script, provided that we already have this direct acyclic graph of pre-signed transactions that form the covenants, right? So if Alice signs a message X with her public key, Bob can use this X element signed at any later time. And we only need that the previous transaction in the script pod validates that this signature is valid by reusing the same public key. So Alice can create a message, and Bob can use it at a later time. So we have statefulness. But if Alice wants to use her own signatures, then there is a problem, because basically she can create forgeries of that signature. So every time Alice wants to use her own signatures, then we have to give Bob the possibility to challenge that and prove equivocation. Proving equivocation is very easy. Just present two values, x and x prime, with their corresponding signatures for x and for x prime, and then you can verify in BitConscript that these two messages are signed by the same public key, and you can punish Bob for this. Punish Alice for this. But it turns out that if you use this scheme, it makes the protocol design kind of complex, because you have to keep in mind that every time you use a value, you have to give the other party the opportunity to challenge. So what we decided, just to simplify the protocol, is do countersigning. So every time Alice signs a value x, then Bob comes and signs x again. So at that point, both of them can use the value x that is signed, and Alice will choose to use the x value that was signed by Bob, and Bob would choose to use the x value signed by Alice. So very easy. So now we have this building block. We can link messages and create a challenge response dialogue. So what Alice is going to do, she's going to sign a value x. Let's say that x is a step number she wants to query for more information, for a hash. And what Bob is signing is the concatenation of x plus the response. And the response will be a hash, probably, okay? So these two values get paired, and you can basically take these two values and put them back in a later stage of the protocol, and nobody can fork that. So now that we have the building blocks, I can tell you more about this BitVMX meta CPU thing. So first, we can do whatever RISC architecture we want, like 8 bits to 64 bits. There is no limitation on that. We can do practically unlimited memory. Like it's bounded by, not really, because we only need a number of rounds, which is in the logarithm of the amount of memory, so we are good. Any number of word size register in our CPU we can code, because we are using memory mapped registers, so it's like memory. We obviously have a program counter, and each instruction can do any number of inputs outputs. So eventually you could also implement a CISC processor on top of this. But we are really interested in implementing a particular RISC-5 32-bit CPU. Why? Because it's super general purpose, and there's a lot of tool chains to use it. So RISC-5 is license-free, royalty-free. It's a specification. It has 32 memory map registers, arithmetic operations. You have a memory operation, loads and stores, a 32-bit memory space. All access are aligned to memory, so that's good, because it saves us to read one additional potential value from memory. So if you want to do unaligned access, you just do it in software. And well, instructions are also easy because they are 32 bits in length, so very, very simple to code. So now that we have the processor, we create a full trace. So when we execute locally the code, what we produce is what we call the full trace, where we write for every single step of the computation these values. For the inputs, we write 3 values. 2 reads, one would be a register and one would be a memory access, if the instruction requires both, and a read of the program counter. And for each one of these reads, we record the address that was read, the value, and this is the difference between other models. We record the last step where this address was written, okay? And from the output, we record the address and the value that is written and the program counter. And there is a smaller amount of information that we call the trace, or the write trace, which it's only the step number and the writes. We don't care about the reads. That's another interesting thing. So now that we have these traces, we can build a hash chain, not a Merkle tree, but a hash chain, where each hash, we start from a fixed random value, like 0, and at this step of computation, we hash the previous step, hash digest, and the trace, only the outputs of the instruction processing, and we build this for the whole computation. So this is very fast. Like, you can do millions of hashes per second. So what is interesting is that you can, for each challenge, you can just run your computation over and over. You don't need to store this information, because you can just grab the information you need. Or you can put some checkpoints in certain places so that you can do faster in the future. But essentially, it needs no memory, only to store temporarily the last steps that each memory cell was used, right? And so there is a verifier decision tree where he chooses what to challenge, and instead of going through the theoretical thing, we'll go into a particular example to show how easy it is. So as I mentioned, at first we have a binary search where the verifier asks for a specific trace step hash of specific steps, and the operator responds with those step hashes. So this is simple. So let's take an example. Let's think that we have only 16 steps of computation. We know that step 0 is correct, so the step hash of step 0 is correct because this is the initial step. And we know that step 16 is incorrect because, if not, we won't be challenging. So we challenge because the last step is incorrect. And so we will ask, obviously, for a midpoint, let's say step 8, and then the operator will tell us the step hash. And in this example, step 8 is correct. So we move to a midpoint between step 8 and step 16. We have step 12, and then we move on this binary search. And finally, we have 2 steps, in this case, step 11 and step 12, where we have some kind of malfunction, right? Something is wrong about step 12. So 2 things can be wrong about the step. Either the right operations in the hash chains are incorrect, like the operator is cheating about what is the result of executing this instruction, so the outputs are wrong, or it could be the case that the outputs are right, but basically the operator is lying about how the hash function operates, okay? So what we ask to the operator in this case is a new challenge where we ask the full trace of that instruction. We only had the hash, now we want the full trace of that operation. So the operator will bring all the read values, each one with this last step that was where this memory address was last written, everything. And now it's very easy to find out where the error is. So if the error is in the program counter, it's very easy to challenge because you have the previous step, which is correct, which writes the program counter. So you only have to show, the previous program counter and a new program counter, and if they are not equal, then the program counter is wrong. If the writes are correct, then we can challenge the hash function. So that's very easy. We only need to code SHA-2056 in BitConscript. We have already done so. Martin here has made an implementation that is below the threshold of standard transaction, and we can even split that in chunks with mid-states. We can make it for very low amount of BitConscript, so we can challenge the hash function. But the worst case would be, that the writes are incorrect because of the reads. Like, the operator is telling us that he has read from memory, but he's lying about the address or the value or the last step. Something is wrong. So the easy thing is, what if the last step is correct, the value is incorrect, and so, but the step 5, here the last step that the operator tells us is step 5, but this step 5, he shows us the step hash, and the step hash is correct, but it doesn't matches the value written with the value read on step 12. Well, this is the easy case. We just challenge that. I mean, we have a good hash here and a bad hash here. One is writing a value, the other is not reading the correct value. Easy, very easy. Well, what happens if the last step value is incorrect? Maybe the prover tells us the last use of that memory was in step 3, but we know from our local execution that it was used in step 5. and a different value was written. So this is the interesting thing. We know that step 5 is incorrect because we have run this locally. And we know that step 11 is correct. So now we are in a scenario which is the opposite that we have at the beginning. At the beginning we had a starting step that was correct and an ending step that is incorrect. And now we have the opposite, a step that is incorrect that ends with one that is correct. And this should immediately raise an alarm. I mean, it's very easy to prove that there is no hash chain possible that can convert a bad step into a new step, into a good step. I mean, we had to break the second pre-image of this hash chain. So, and we can do even better. Like, we already have some challenges previous to step 11 that tell us good steps. So we run a new binary search only between those two steps, the incorrect step and the correct step, until we find a magical recovery of the computation, right? A place where there is an incorrect step followed by a correct step. And now it's very easy. We just challenge the hash function. Like, it's impossible to come up with a different write to registers or memory that can turn a bad step hash, in this case step hash number 6, into a good step hash, which is step hash number 7. So basically, we've solved all the problems of memory access, memory writes, execution. Oh, I didn't mention, but if the writes are incorrect and the reads are correct, we just challenge the step of execution. That's also very easy. Just one step of processing, and we can show that this instruction does not create the right outputs. So we've covered all the cases. There are some other cases related to how to access the program input and how to access the program ROM, where the program is stored. That's on the paper. You can read about that. But this is the good stuff is this. We can improve it by doing, instead of doing a binary search, which was something that Robin did in BitVM1, we can do an NRE search. So instead of the prover giving just one middle hash or just one hash, he can give several hashes equally separated in the space, and then we can make a trade-off between the round complexity and the cost, the transaction cost. So it's tunable. We can find a sweet spot where we feel that we can spend that amount of money and do not delay the program the protocol much. And we can do even better. Instead of transmitting the full step, we can just transmit the small prefix of each one of the selections in the space. Tomorrow at 10 o'clock, Ramon and Javi will be giving a workshop where they will code this and show us how to do this binary search in BitConscript. So you will be able to play with this with their help. So how is BitVMX compared with BitVM in a particular stance where we want to verify a snark, which is generally the most common case? So if we take the gate-based, BitVM0 protocol, and this is just a theoretical comparison, it's not very important in practice, it's much better. Like, it would take weeks of preprocessing and terabytes of storage. But if we compare with BitVM1, we can do it with a lot less preprocessing, basically almost no preprocessing, and just with much less memory. And with a little less on-chain cost. Like, we estimate this because BitVM1 was never built, these are only estimations, right? But we estimate that it would cost like 300 kilobytes in BitVM1, and we think we can do with 200 kilobytes. And another interesting comparison is against BitVM2, which also not finished, but is super promising. And it can solve the dispute in just one round, but you need to post a huge amount of information in the blockchain, like more than 4 megabytes of data. So this may cost you 100K maybe in transaction fees. It may be very good for maybe for multi-party, but yeah, it depends on the use case. But generally, it would cost a lot, and you would only use that for very high amounts of money. And of course, we have a Bitcoin opcode wish list. Like how this could be improved if we have more Bitcoin opcodes. Well, basically, I'm not going to the detail, but basically, this would take, if we had all these opcodes implemented, like it would take like 20 kilobytes to solve any dispute, from 300 kilobytes to just 20 kilobytes on chain. So it will very cheaply. At today's cost, it can be like from 3K US dollars to yeah, a couple of $20 or maybe. So we have a roadmap with the resources and the people we are working on this to finish this in 1 year. We've published the BitVMX paper. It's ready for you to download now in the BitVMX website. Please take a look and send us your comments, your new ideas. Please come and contribute to the Telegram channel. The next paper that we are already working on is about extending the two-party protocol to n-party protocol. And there is a lot of open questions and very interesting challenges and how to do that very efficiently, minimizing the security bonds. And then we will do a release of this code, and releases we will try to do on a periodic basis, right? But we plan to do a full release of the n-party protocol, and finally a last release with some optimizations by the end of the year. This is a, I mean, maybe you want to attend. This is a Bitcoin Rootstock meetup that is happening today. And if you want to learn more about Rootstock sidechain, please come to this meetup. I'll be there to answer more questions about BitVMX. Several people from the BitVMX team that are collaborators are here, and they will be there too. So we can have a great chat about BitVMX here. Yeah, that's all. Hope you visit our site and come to our Telegram channel. Send us your comments or proposals, or if you want to code, we will welcome your contributions. And I don't know if there's time for Q&A or we are done. Okay, 2 questions. Is there any? Yeah. Well, the closest you can have without interactivity, which means, yeah. Yeah. Yeah, I mean, if we have covenants, and then if we have like multiplication, then I think the best approach would be just to do it in a single script, like split in parts, like BitVM2 idea, and then you would be able to do it in 1 round. But I mean, Rootstock, from our perspective, we cannot wait until that happens. Like, we've waited so long for snark verification to be on Bitcoin. I mean, we really want this to happen, the new opcodes, but we are moving forward at full speed because there is a lot of users and active users in Rootstock that they want a more decentralized reach. Okay? One more question. John?
Clarifying question about the comparison chart. You noted that BitVMX puts 200 kilobytes on chain.
Yeah.
Is that over the entire string of challenge and response transactions, or is that per?
Yeah, it's about 300, and it's the whole protocol. So it's very short amount of data. And you can do some trade-offs between data and round complexity, right? By doing these NRE searches. These are estimations. We haven't coded, but in paper, these are the amounts. Okay, thank you very much, and to the organizer, thank you.